PolyTalk 2013, Analysis of the Heat Affected Zone during Welding. The basic welding process fuses two pieces of metal together with the aid of a filler material. This happens at extremely high temperatures, and you get the zones! The zone in the center is the fusion zone. This zone occurs with the liquefaction of the base metal in addition with the filler material. The next zone out is the heat affected zone. This is the zone that we're concerned with. In this zone, there is no fusion with the filler material, and instead heat transferred from the fusion process affects the microstructure of the material welded.
There are two factors that determine the size of heat affected zone. Material's property and welding method are the two factors. Higher thermal conductivity will dissipate heat faster and it will make smaller heat affected zone. Also, welding method with low heat input also makes heat affected zone smaller.
Oxy-fuel welding has a low heat intensity. This requires a high heat input for the process as well as slow welding speeds. On the other hand, laser welding has a high heat intensity, meaning that the process can happen faster with higher travel speeds and the heat input is a lower rate. This means that laser welding can produce a smaller heat affected zone, when oxy-fuel welding creates a larger heat affected zone.
Here are two macro scale examples of the heat affected zone. You can see in the center of each where the weld bead lies, and that would be the fusion zone. Just outside of that is the heat affected zone. It's denoted by the discoloration. As you can see, the heat has altered the metal. And you can bet that if it altered the optical properties, it's going to alter the microstructure as well.
The microstructure properties change due to the diffusion in the heat affected zone, as well as phase transformations when cooling from higher temperatures and grain growth.
Zooming in on the microstructure reveals three distinct regions. On the far left, you have the unaffected parent metal. In the center, you have the grain coarsened area in the HAZ. And on the far right, you have the weld metal. The grain coarsened area is due to the heat from fusion of the weld metal. That heat allows atoms to diffuse across long distances. These long distances correlate to larger grains, and as you move further towards the parent metal, the temperature is cooling. As the temperature cools, the atoms can no longer diffuse across long distances, resulting in a smaller grain structure.
There are various problems that arise due to the heat-affected zones. The uncontrolled diffusion that occurs during the weld allows for grain growth, causing a grain size gradient within the material, altering the parent material's mechanical properties within the HAZ. One mechanical property affected is strength. As the grain size increases, strength may decrease. Also, at grain boundary interfaces, there is an increased risk for brittle fracture. Uncontrolled diffusion is the source of the heat-affected zones. Understanding that difference in temperature is the driving force behind diffusion will help us better control diffusion during a weld. At the high temperatures necessary to weld, there is plenty of energy for diffusion. This energy comes from the large difference in temperature between the parent metal and the weld. The solution to better controlling the diffusion occurring between the parent metal and the weld is to minimize the difference in temperature. By preheating the parent material right before welding, the difference in temperature is reduced. A more uniform grain structure or smaller grain size gradient will result. To recap, welding allows uncontrolled diffusion resulting in the HAZ. The uncontrolled diffusion and grain size increase alters the mechanical properties of the material. To maintain properties of a parent material during welding, controlling diffusion is essential. Reducing the difference in temperature between the parent material and the weld by preheating will better control diffusion and result in a more uniform grain structure.